And we're rolling. And we're rolling just like that. So it'll record it as we go. And when we're done, we hit end and save it to a file and put it on YouTube or whatever, and we're good to go. All right, so if you missed today, just kind of follow along on YouTube and you'll be all right. All right, so for everybody else, what we're going to be doing today is piston speed, okay? So you've seen, we've been talking about engines for a little while. Here's a nice little GIF or whatever you want to call it of the piston going up and down, up and down, up and down. But my question for you today is, how fast is this piston going? That's my question for you today. How fast is it? Well, I don't want the angular velocity or the angular speed. I want the linear speed. If that piston were not going up and down, up and down, and up and down, and it just went straight, okay, what would the speed of that piston be? How fast would it be going? Give me some, throw some numbers out there. You think? Yeah, maybe. That might be about right. I don't know. We're going to find out exactly what that is and how we can calculate that today. Why do you think knowing piston speed would be important? So it doesn't melt. We don't want that to melt. Right? You pay a lot of money for these cars. You pay a lot of money for this thing. So we don't want it melting. So this piston is going up and down, up and down, up and down, up and down. But what we're going to do is find the linear speed to where instead of going back down, it's just going to continue straight. If it were to continue straight, how fast is it going? Because that speed is how this piston is rated. They make different kinds of pistons. Anybody know what kind of different pistons they make? Forged, cast, aluminum. Okay, yeah. So they make some different pistons out of different things. We're going to look at 3 different pistons today. We're going to talk about how fast they're capable of going and how we calculate that speed. So think about what's happening here. Crankshaft's going around and around and around. That thing's going up and down, right? So what kind of elements do you think will be important for calculating piston speed? Oops, that's not it. Not that class. This class. Okay. What concepts do you think are going to be? Oops. What concepts do you think are going to be important for you to find out the stroke? Because you saw it. That's fine. The RPM because you probably saw it. Okay, that makes sense. And that's just about it. That's it. That's about it. Stroke and RPMs. Okay. So it's pretty easy. So think about the concept here, and some of the people in the video can't see this, but that's all right. So the one full crank, right? Let's say I'm at the top, right? So I'm at the top of my crank. It goes halfway. Now I'm where? At the bottom, and it goes back to the top. That's 1 revolution. So it goes top, bottom, top, 1 revolution. Top, bottom, top, 2 revolutions. Does that make sense? So give me an example. If we were going 1,000 RPMs, 1,000 revolutions per minute, how many times did it go top, back to the top? Well, yeah. Well, it went 1,000 up, downs, which is 2 of those distances. Would you agree? So that cylinder, that swept distance in the cylinder is 2. So for every 1 revolution, it goes twice that swept distance. Make sense? So the formula becomes pretty simple. It becomes 2 because it goes from top to bottom to top in 1 revolution times the stroke, because remember the stroke is from top dead center to bottom dead center, right? So it's 2 times the stroke times out however many revolutions per minute, okay? And that's how you calculate piston speed. You can put that right under that piston speed formula right there, but this is going to be in a unique unit that you're not going to like and that you're not going to recognize. What kind of units do you think this would be measured in if we went from, if we were considering the stroke and the revolution per minute? Okay, so you're thinking feet per second, right? But what is my stroke typically measured in? Inches. So it's inches, right, per... His revolutions are being counted per what kind of time? Minute. So this would be inches per minute. And now you might be looking at that like, inches per minute? What is inches per minute? Like if I told you 5,000 inches per minute, would you be like, is that far? Is that fast? I don't even know. That's not something you're familiar with, right? When it comes to speed, you're probably only familiar with one kind of measurement. And what is that? Miles per hour. So what we need to do is we need to get into miles per hour. So there's a pretty easy conversion. Oh, where'd it go? Okay, so let's say we didn't want to measure this in inches, but we wanted to measure it in feet. Maybe that will get you closer. And pistons are ranked or classified by feet per minute. That's what they use the classification for, is feet per minute. Okay? So how do I convert my formula to turn this into feet per minute instead of inches per minute. How do I do that? Yeah? Okay, close. So if I'm in inches, let's say it's 3 inches, but 3 inches is how much of a foot? How much of a foot? A fourth. It's a fourth of a foot. So how do I turn 3 into a fourth? 5 by 3. 5 by 12. Exactly. So we're going to alter our formula a little bit. We're going to call it 2 times the stroke measured in inches divided by 12. So you were close. It's just a division. Times the RPMs. Okay? Now, you might be looking at that like, I don't like that fraction. I don't like that fraction. I'm going to change that a little bit, switch that fraction up a little bit. So what do you know about if you have a 2 on the top and a 12 on the bottom? What are you able to do? It's like cross multiply, but it's called cross cancel, right? So the 2 becomes a 1 and 12 becomes a 6, and there's your formula right there, boys and girls. You just get your feet per minute is going to be the stroke length measured in inches times the RPMs divided by 6. And that's your formula right there that we're going to use for most of it. Now, you're still probably not going to be super familiar with this, and I'll show you how we switch it into miles per hour. That's not too bad. But let's just start by doing an example, and then we'll go into that. Okay? So everyone got that copy down? Anybody got questions about how we got there?
We write it right here.
Yeah, just right under that piston speed formula thing. Yeah. Yeah, well, all right, so our final equation is just this right here. That divide by 12 is just how you switch it from inches to feet. So this is all we really need right there. Okay? I just wanted to show you how we got there. And sometimes I can throw that equation out there and you're like, how the heck this is how you got there. Okay? All right, so let's try an example together. Nope, not that. All right, let's talk about this guy right here. We got a 3024, which has a stroke of 3 inch and a maximum engine speed of 6,000 RPMs. Any of you guys noticed on your tachometer where your RPMs measure that it has those little red lines in there? What are those red lines? Why do you think those are there? Like that's the sweet spot, right? That's the sweet spot. You gotta get there. No, that's not the sweet spot. That's the danger zone, man. You don't go into the danger zone. They make it red like, ooh, I don't like red. No, that's not what it's there for. That red line, that red means danger. Don't go there. No. Okay. So, that means this thing has a red line of 6,000 RPMs. We'll talk about how we calculate that in a sec. You're going to do it on yourselves, okay? Okay, so what is the mean speed in feet per second? So let's do the formula. Remember the formula is this, feet per second. So that speed is measured by going the stroke times the RPMs divided by 6. That's the formula. So let's try it out. What's my stroke in this example? It has to be measured in inches. So what is it? 3. So we got 3 times 6,000 divided by 6. Well, that's a nice one. We don't even need a calculator for that one. It's so easy. Yeah.
That's just FPMs, there a difference?
That's supposed to say feet per minute. That was my bad. That's a typo on my part. That's supposed to be feet per minute.
So that's supposed to be FPM too?
Yeah. Yeah, it is. That's my bad. That's supposed to be feet per minute. That's my bad. Okay, so let's think about it. So the 6,000 and the 6, that'll cancel to 1,000. We know that, so we don't even need a calculator. That becomes 1,000. And 1,000 times 3 is 3,000. So we're at 3,000 feet per minute. And that's our measurement there. 3,000 feet per minute. Okay? So that's pretty easy to do. So that's how fast it's going. Now, you might still be looking at that like, wow, 3,000 feet per minute. Is that fast or is that not fast? What do you guys think? I mean, like, how fast is that? Is that pretty fast? Like, give me a miles per hour. How fast do you think? 50 or 60? 40, 45? Let's find out. All right, let's find out. So let's find out what it is in miles per hour. So this is a pretty easy conversion. Well, that's what we're going to kind of do. So let's find out how we do that. So if we know it's 3,000 feet, so feet are on the top, per 1 minute, that's how you kind of represent that relationship, minute, not a minute. All right? And we wanted to get the feet to turn to miles. Do I want the feet on the bottom or the top of my next fraction? I want it on the bottom because I want to cancel. So the feet goes on the bottom and the miles goes on the top. All right, so how many feet are in 1 mile?
5 tomatoes.
5 tomatoes. Oh, hold on.
5,200.
Yes, 5,280. That's it. Okay, so there you go. So now I know my feet are going to cancel, which is good because I didn't want that to be there. But I have to do one more conversion because I'm in minutes, but I want to go to, I want to go to hours. I'm going to go miles per hour. So I want minutes to go on the top, right? So minutes go on the top and hours go on the bottom. So 1 hour has 60 minutes. We know that. So now my minutes will cancel. And now I'm like there, right? I'm there. So I got 3,000 times 60 divided by 5280. Okay? So you remember fractions, you multiply straight across the top, straight across the bottom. That's your answer. So that could all go in a calculator all in one fell swoop, and you'll be done. Let's see. So we got 3,000 times 60 divided by 5280. What'd you get? Yeah, that's not good. We want this as a fractor, as a decimal. Yeah, 34. So I got 34 point something miles per hour. Okay. So is that fast? That's pretty fast. I mean, it's pretty fast if you're driving. I mean, it's not that fast if you're driving, but think about this piston, right? This piston's going through a metal sleeve, and it's touching the whole time. There's little flanges on it that are touching, and it's dry. So it's got constant friction at 35 miles per hour going through a sleeve. Is that a lot of? What's that going to do? It's going to get a little hot, right? It's going to get a little hot. Okay. Now, if I was going 35 miles per hour through that tube, or if I was going 80 miles per hour through that tube, wouldn't that be like really hot, right? That'd be a lot of friction. That'd be a lot of heat. That'd be a lot of melt. That's not what we want. Okay? So our goal is not to make that rev too high because then this is going too fast through there and that gets hot. And that's not good because these can only get so hot. How hot can they get? That's what we need to talk about. So how hot can they get? So the question is, you can find out how hot they get, and what I want you to do is write down these numbers next to it. We got 3 types of pistons here. You got your cast piston. That's what's mostly stock. Unless you're buying like a Ferrari or maybe even a Mustang or a Camaro, they might have forged pistons. But this would be your forged. This is not the same order on your paper. Unfortunately, sorry, I mixed them up. And then this one is I can never spell this, so let me cheat. Hyper say it one more time. Hyperkinetic, something like that. They sell these you could get these at like Summer Racing, but nobody will ever need this. Well, maybe you might get into it, but I doubt you'll need it. All right. So why don't you need it? Because your cast pistons, okay, hypertectic. Your cast pistons will go at 3,500 feet per minute. You might want to write that down. A cast piston, you can kind of tell if it's cast. It has that dullish metal. It's not alloy. It's not like flesh. So that's a cast piston. That's a cast piston. That's a big one, but that's a cast piston. Your forged pistons can go a lot faster. They can go at 5,500, and they're a little shiny. They're more like this. So they got a little bit of a shine to them. Okay. So you can buy those, and that'll serve for what most people need. Okay. If you ever decide you want to be a dragster, you might need to get these fancy pistons, which go up to 7,200. And that's about as fast as you will ever need them to go. They will never need to go faster than that. We'll talk about why later. Okay. That's as fast. There's no point in going faster than that. And we'll talk about why the physics and why it doesn't matter. Huh? You can get crazy. It won't. We'll talk about it in a sec. The last question on your page is this question right here. Why doesn't fire? It never does. And it has to do with physics and the way how fast air can go. Okay? There's no reason for it. So if you ever saw something that was higher than that, they were just trying to advertise something higher than that, that's a gimmick scheme. There's no point. Okay? So let's talk about what we're going to do with some of these engines then. So first off, that 302 Ford, it's going at 3,000 feet per minute. Is that okay for his cast pistons? Yeah, he's okay. Okay, he's okay. All right, so let's talk about a Formula One. How fast does a Formula One car go? They're going fast, and they run really high, right? Well, anybody know what their rev limits are?
No.
18,000. 18,000 rev limit, okay? But they're also limited on the size of their engine. Anybody know the size of the engine? 2.4. 2.4 liter engine. Can't be any bigger than that. And they have specifications. They have a lot of restrictions on what the engine can be. But here comes a Formula One engine. It has 1.6 inch stroke, and it can rev up to 1,800 RPMs. So how much faster do you think that's going to be? That's going to be like crazy fast, right?
Well, you're saying 1,800 like 1,000.
Or I'm sorry, not 1,800, 18,000. 18,000 RPMs. So we're thinking this is going to be crazy fast, right? Well, let's do some math. Let's find out. Okay, so, all right, so the feet per minute, and I messed it up again. It's supposed to be an M. Look, typos all over the place. All right, so feet per minute is going to be the stroke, which is 1.6, times the rev limit, which is 18,000, divided by 6. Okay, well, that's a simple problem. Let's just bust that in the calculator, see what we get. So 1.6 times 18,000. Okay, divided by 6. I got 4,800. So 4,800 feet per minute. So, can they use cast iron or cast pistons in a Formula One car? No. Can they use forged ones?
Yeah.
Technically. They don't, but technically they could, right? But is that a lot faster? Is that like a lot faster than that 3024? I mean, it's faster. The 3024 was going at 300 or 3,000. This is at 4,800. Did you expect it to be higher? Okay, so did I. But why do you think it's not so high? Because the stroke. That's key there, guys. And the stroke is the key to this whole lesson. The smaller the stroke, think about it, right? So here's two situations. You got stroke 1, little bitty guy. Stroke 2, little bit bigger guy, right? And now every turn, this guy is going this much distance, right? But every turn, this guy is going this much distance, right? One turn, one turn. So who's going faster? This guy. He's covering a lot more distance per turn than this guy. So he has a little bitty stroke, which allows him to go, right? Real fast. Lots of little mini power strokes. Okay? Does that make sense? Yeah. That's free of charge. Okay? So little mini stroke means you can run that thing a little bit higher on the RPMs. And they have the advantage of using very exotic materials that don't overheat and stuff like that. But they run really little strokes. Okay? All right. So let's talk about how many miles per hour is that then? Let's work that out one more time. What's the miles per hour on this bad boy? So we have 4,800 feet per 1 minute. So we know if we want to clear the minutes, we put the minutes on the top. We put the hours on the bottom. So 1 hour has 60 minutes. And if we want to clear the feet, we put the feet on the bottom. We put the miles on the top. 1 mile has 5,280 feet. So all we got to do is start canceling. Like that. Okay, so feet, minutes, now you're left with miles an hour. So you multiply that out, you're going to get a number. Anybody got the number? 54 miles per hour. So that's a little bit faster, but it's not really that much faster. Or is it a lot faster? I don't know. If you remember, friction, going through a metal sleeve, 35 miles per hour or 54 miles per hour. It's almost twice, right? So that's twice as much friction, twice as much heat. So yeah, that's a lot. Okay, so that's a decent difference. Okay, yeah. What did I multiply? I multiplied 4,800 times 6 divided by 5,200 or 5,280. So all across the top, all across the bottom. 5280. Yep, same concept. Use the same concept. Yeah. If you wanted to, if you really want to make a ratio there, do this divided by this, get that number, and just multiply your number by that. It'll work every time. Either way, just know how to manipulate the variables. Though. That's what I want you to do. As long as you can manipulate the units, so you're good. What's up? By 60, and then divided by this. right? So here you go. Here's your colors here. Yellow times yellow divided by green. There you go. Okay? Because all the rest are ones, so they don't matter. 54 miles per hour, or I want it both. I want it both. So you got both. Yeah, there you go. I want both. Okay. So let's try this example out. Let's see if you can figure this example out without me helping you. All right, I'll give you a second to try this on your own. All right, you got a 350 Chevy with a 3.5-inch stroke, cast pistons. Can it run safely at 6,000 RPMs? That's the question. Okay. So run the number, find out the feet per minute, and see if it's okay for cast pistons. If it's not, right now, and then try it for 7,000 RPM. So try both ways. I'm going to pause the video, and we'll come back to you in a second. I don't want the video to get too bad. Okay, you're back. All right, so we ran out both examples, 6,000, 7,000. You can see at 3,500 feet per minute, we're okay. That's just fine. We're fine with that. On 4,083, that's no good. No good. Okay? For cast pistons, because cast pistons can go up to, what was it, 3,500? 3,500. Okay? So this is okay. This is not okay, so don't do this in the parking lot. Don't do that, or you'll be sad. Okay. Don't do it. I'm trying to warn you. Okay?
The only good ones.
Yeah, I don't know. I wouldn't suggest it. Okay? Okay, so there you go. How about this Audi R8? Oh, I'm sorry. You're still writing it down. I was excited. There was an Audi coming up. It has
Great googly moose this Audi.
It's a V10.
Is this right though?
It's the R8.
Everybody likes spiders.
Okay, you did? That's for a Cummins. That's for a Cummins. Okay, Audi R8. That's maybe one of my dream cars. We'll see. It has a 3.3-inch stroke, but it can rev up to 8,500 RPMs. So what kind of pistons better this thing better have? What kind of pistons in it? Let's find out. So 3.3 times 8,500 divided by 6 gives me 4,675. So they better put forged pistons in it. Yeah, so feet per minute. So that's pretty fast. But remember, I'm giving fast piston speed a bad name. You want it to go fast because the faster it's going, that means it has more power strokes, right? More power strokes means more power. That's what you want, but you just don't want it to melt. So you want the engine to have high performance, but you want to do what the engine is designed to do. You don't want to do what the engine is not designed to do. Okay? So there you go. Are we done? We're not done. What is this guy? Oh, that's Mr. Sanders. Hey, Mr. Sanders. Yeah. Okay. This is a good one. Yeah. So you gotta. I googled what engine has the biggest stroke, and the one of the popular ones that came up was this 4.5 liter Bentley, which has a 5.5-inch stroke, which is like ginormous, right? So it's huge. I don't know why they would do that, but they did. So, and I love a Bentley. I wouldn't mind driving one of those around. My dad had one. I would definitely take it for a joyride. But I wouldn't be revving that way up to 6,500. But let's say your dad has a Bentley with a 5.5-inch stroke, and you rev it up to 6,500 RPMs. You better hope it has what kind of pistons. Let's find out. So 5.5 inches. That's the stroke, and you're going to multiply it by the RPMs. And then we're going to divide it by 6. Anybody do this ahead of me and get a number? Yeah, what number did you get?
5,958.
Woo! Okay, 5,958 feet per minute. So what kind of pistons better it have? Yeah, those hyper pistons. Okay? So it's got to have those pistons. Otherwise, I'm going to be melting Dad's Bentley, and he's not going to be happy. But he's not going to be happy at all. Okay, so that's how you do that one. It's pretty easy to do. What we will do tomorrow, and then on the video, I'll just pause and do it with the next class. We'll do desired RPM limit. So if you ever wondered how did they get that red line, how did they calculate that? Well, it's a slight manipulation of the equation that we're using. Okay, so we'll do that tomorrow for the video. Just keep saying I'll do it. Okay, I think we're back, and I think this is where you were. So let's see, establishing RPM limits. So it's pretty easy to figure out where that red line is going to be. All you have to do is do the desired piston speed times 6 divided by the stroke. And then that'll give you the RPM or that red line that should be on your tachometer. Oh, I'll get that in a sec. Alright, give me 1 sec. I'll get that for you. You're probably going to have to wait until Alex is done first. Oh, 1 sec. Let me pause your video here for a second. Alright, sorry video people. I'm back. I know it's not going to interrupt him.
That's a lot.
Alright, so let's see. Let's see if we can work this problem out here. It's pretty easy to do. We're going to do a 427 and it has a 3.76 inch stroke, and we want to impose a limit of 3,800 on the piston speed. So RPM equals 3,800 times the times 6 divided by stroke, which is 3.76. And you just got to type that in, and then you're done. Let me make sure I have that right. Yep. Okay. All right. So we'll take that in the calculator, and then it'll tell us where a rev limit should be to stay within that tolerance of piston speed. So multiply that there, divide by 3.76. That's the stroke, and that gives me 6,060. So 6,063.4. Okay. So my RPMs need to stay within that range there in order to not go beyond this piston speed here. Okay. So that's how it works. So if you know your type of pistons you have, you can work backwards and figure out what your rev limit should be or how they calculated that for your particular vehicle. Okay, so here we go. NASCAR. NASCAR has limits on your displacement. If you took full advantage of the bore, which has a restriction, I think it's 4 1/8, and if you took full advantage of that bore, and that would limit you to a 3.25 inch stroke or 3 1/4 inch stroke. So if they decide that the team wants to keep the piston speed within 500 feet per minute, then what would the RPMs have to reach on the straightaway, or what would that RPM limit hit on the straightaway on the last line here? So, well, pretty easy to do. RPM equals 5,000 times 6 divided by stroke. See, same formula. You're just switch it up a little bit. So let's see what that is. 5,000 times 6 divided by 3.25. I get 9,230. That's right. Yep. So 9,230 RPMs. Okay, so they need to keep those revolutions below that, and then they're okay. So as long as they don't go over that, they'll stay within their piston speed. Won't blow end up blowing an engine or anything, and they'll be able to ride it right out. Okay, last problem is all for you. Real life situation. What you need to do is you need to Google what your stroke is. So Google your stroke, okay, and find out how long it is. If you can find the type of piston, that's even better, but if not, that's okay. Just use a cast, if not, because it's probably a cast piston, which has a limit of 3,500, just in case you forgot. Okay? Use that information and find out what your rev limit should be on that tachometer. Like, so where is your real red line? Where should you not go beyond? So you'll find that stroke, work backward, just like the last two examples, to stay within this limit, and find out what that red line is. And that's it. Last problem, why don't you ever see a value exceed the 7,200? Well, because when that fuel and air ignites and that combustion happens, it expands, and it can only expand so fast. That's pretty close to what the limit of what it can expand at. So you're not going to see a piston speed much faster than that. So that's a little heads up on that. All right, we're done.